I don't think I really decided. Around. You win it less. But I looking at it. So, I think the study paid off, but man, those. I can imagine. I was doing all the stuff before. Our professor are great.
All right.
Yeah. I've been using ChatGPT. I did it.
All right, looks like screen share is working. I'm just gonna double check on my audio channel and then we can get started. Okay. All right, so it works. All right. All right, looks like the recording is working. You know, the screen is being recorded, the audio is all good, so I think we should get started. There may be more people joining us, you know, remotely, maybe. But as I pointed out earlier, this homework assignment is only 4 points out of all of the points, okay, in all the labs and homework assignments. So point-wise, it is not a big deal. You know, if you don't turn in anything, you know, it's not a big deal. What does matter is that you give it a try. Because, you know, in the attempt of trying to get this to work, you are going to have to exercise everything that you have learned and everything that you also need to know for the final exam. Okay, now not being able to get the program to work can be there can be many reasons. You can miss one little thing, you know, that one little 1+ thing, you know, if you miss that, depending on the context, the program is not going to work. I mean, you guys already know that in programming, there's no such thing as, you know, anticipating how long it is going to take to write a program. Because if one single thing breaks, it's not going to work. So it's not, in some way, mechanical engineering projects can still be kludged, okay? Because you can use hot glue, you can use various, you know, items to kind of hold things together, right? You know, to get it, you know, get past, you know, the test. But in programming, if one thing doesn't work, it's just not going to work. So, so don't beat yourself too hardly, you know, if you could not get the program to work. So what we'll do is I am going to work on that program today, and I really do not remember the solution. Okay, so I'm deriving everything from scratch, and I'll be explaining at the same time. And hopefully my implementation will not work, because that way I can also show you guys how to debug a program. I know this is the last lecture of the entire, you know, CISP310, but the technique of how you test a program and how you reason out why it is not working is universal to all kinds of programming projects. So that means, you know, some of this will also transfer to your other types of your programming. All right, so we'll go ahead and get started. And I'm going to announcements to get to the zip file, because I think I restarted my computer, so the zip file may not be with me anymore. So where did I put that? Tree.zip, there we go. And just download this, SafePoint Gas, stash it into the temp folder. Oh, okay, I guess I have it already. Doesn't matter, I'll go ahead and replace it, start from scratch. And we'll go here. Oh, today I was informed by my dean that as it turns out, even after the last day that you can drop a class, I can still drop people. There's actually a special form and a special procedure for those special individuals. I did not know that. So I will amend my syllabus. So next semester, I will have, you know, more interesting, you know, policies for that class. Yeah. I already took a look. And we will talk about that after class. All right, so tree is already here. Okay, so there we go. So we got tree.c, okay, that's the C program that actually compiled and ran. And then we have tree.ttpasm, which is the assembly language implementation of the same program, or we want it to be the same program. All right. So what I gave you, in the TPP-ASM code is the very we need to write this program. So what I did not give you is the definition of node. So I'm going to put it here, the definition of node, which is a structure. So the typical way that I do this is I will spell out node underscore value. This is the first member of the structure. It has the displacement of 0 from the beginning of the structure. And then we have the left-hand side, which is the second item. So it's going to be node value 1 plus. The 1 here is referring to the size or the number of bytes the value is going to take. And then we have node underscore r. That is the third item. So it's going to be the second item 1 plus. And once again, this one here is referring to the size of a L member of the structure. And then last, we are going to define the size, even though I think in this program, we don't need to know the size. We'll just go ahead and define it anyway. So that is going to be node R1 plus, because node R is referring to the offset to the last member of the structure. And then when we add the size of the last member of the structure, then we have the size of the entire structure itself. All right. So that's the definition that is going to come in handy. Let's see. So we have all the static local variables already defined here. And the only thing we need to do is to define traverse. All right. So I'm not sure how you guys started with this program. The first thing I would do with this program is simply to put a halt here. In other words, I would have the program to stop right at the entry point of traverse. So that this way I can take a look at the stack and find out what is on the stack. Can I identify the local variable R as well as APTR in main? Can I identify the arguments main used to call traverse the first time? Can I find the return address? Can I find all of those items? Okay, and I would also use that opportunity to look at the parameter in traverse and see what kind of a double pointer is it? Okay, what is array? Array is a double pointer. So what pointer does it point to? Okay, it points to APTR in main. And then what is APTR itself pointing to? It is pointing to the beginning of R as an array. So those are the things that I want to confirm. Do you guys want me to see, do you want to see all that stuff, before we even get into the traverse subroutine? I think we have enough time, so I think we can do that. Yes, okay, let's do that. So exit out. Well, I don't have to exit out. I'll just start a new tab. And this time we'll go to River Spider. And I'm not sure how many of you, spend the time to get it to work. I know there's a little bit of work involved, but it does help to streamline the whole process. But even if you don't do this, it's still doable. Okay, you can still do it manually. It's just a little bit more cumbersome to do it. All right, so we are waiting for Google Drive to process all of this. Okay, object load is good. It's simulating, it's all done. And all right, so now we can switch back to the browser to take a look at the output of the trace analyzer. All right, so we'll focus on analysis. And there are a few things that are kind of important here. The trace itself is not really long. Okay, it is. Oh, this is not good, is it? Because it looks like it is stuck in a loop of some kind, and then the stack pointer kept decrementing. So that's the same thing that you observed. Okay, well, let's find out what is Well, first of all, is this the program that we are debugging? That would be the first question that I have. And we go to source, and then we check out. Nope, it is not. Why is it not? Because I'm not seeing the definition of the node. So this is not the same program that I was trying to debug. Let's see. We'll figure this out. All right. Oh, okay. I see why. What does that mean? I did not save the file. I made changes. All the changes are here, but I did not save the file. And then Reverse Spider just goes like, well, since you want me to use this file, they have no idea that I forgot to save the file. Okay, typical of myself. There we go. Save the file, and then we're going to run it again. Hopefully this time it will stop at the entry point of traverse, and then we can take a look at what is on the stack. There we go. Okay. And then we switch back to the browser. We go back to analysis again, and this time it should end fairly quickly, like that. Okay, so that's looking a whole lot better. So now the question is, what are we supposed to look at? Well, the first thing is, do we know where to find each item on the stack? Okay, so that would be the first question. I'm just thinking of what I should use to illustrate it. I think I know how to do this. I'll use another Google Sheet to do this, and I'll put it into the shared folder. So this way you guys can access it right away. So it's in the shared folder, and I will name it under today's date. Okay. And it shall be called 2023-0511, and this is the Traverse homework assignment. Okay, so what I'll do is I'm going to kind of just look at a few addresses here. Now, this is really the inefficient way of doing this, to kind of list all the locations. There's a faster way to do it. It's not necessarily a better way, it's just faster. So if you want to learn the faster way to do this, it is going to be hex, dec to hex, dec to hex. There we go. It means decimal to hexadecimal, which is base 10. Okay, the base 10 part is really kind of irrelevant, but it's converting to hexadecimal. And what we are converting is going to be the column 256 minus the column row number. There we go. There we go. And then we can just look at the first bunch of these items. So we want to be able to know which location is used for what purpose and what is at that location. In other words, column A is only giving you the addresses. We're not, the column B will give you the content at those locations, and the column C would be the comment on those particular items. Are we doing okay so far? Okay. So now I have to switch back to the code in order to do an analysis to find out what is where. So I'm just going to execute the program by hand until I get to the halt instruction. So if someone is thinking, isn't that a lot of trouble doing this by hand? The answer is, you kind of have to do it, okay? Because that's the whole point of writing code like this, is for you to kind of hand trace the whole thing and understand what each instruction is doing and what is the effect of executing those instructions. So we start with line 1. Line 1 is no up, doesn't do a single thing. Line 2 also does not really do a single thing, because register B starts with a value of 0 anyway. And then we have a call template. So everything from line 3 to line 6 is basically typical of a call sequence. We push a return address on the stack, and then we continue execution over at the main. Okay, so here's the question. Does it do anything to the stack? And it does do something to the stack, because what happens when you call a function? You have to push the return address. That's the minimum that the caller has to do. And the return address is now on the stack. So that means location FF, whatever it is the return address of main back to this entry code here. Does that make sense? Or you can say it's the address of this particular halt instruction on line 7. Okay, so knowing that, we're gonna go back here and say whatever is the content here, I'm not too concerned about it. This is the return address, okay? Return address to line 7. Okay, that's all I need to do, okay? Because it is not super important from the perspective of the rest of the program, particularly traverse. Traverse is completely isolated to this location. It does not need to know what is at this location. So now we look into main and find out, okay, once we get to main, what are we doing? So main is here. So the way we allocate the location, the bytes in main is we have 2 local variables to allocate. The local variable that has the least location is R, which is in an array of 5 bytes. And then we also have APTR that is only using 1 byte because it is just a pointer. It is just the address of something. So together they should use up 6 bytes. Are we doing okay so far? Okay, just kind of, so you don't have to visualize because I'm now going back here and I'll show you what it means. So we have these 6 bytes allocated. Okay, there we go. We have these 6 bytes allocated. The first or the lowest of these 6 bytes would be allocated to, I cannot remember, R, which is an array of 5 bytes. So this would correspond to the first byte of R. This would be the second byte of R, the third byte, the fourth byte, and then the 5th byte, the last byte of R, and then this would be APTR. And those all belong to main as a function that is now called. Are we doing okay so far with this? Right? So after all of these allocations, the stack pointer will, at least for now, be pointing to this location because that's how we decrement the pointer. We basically decrement it by 6. So then we go back to the source code here. This is doing the allocation. So by the time we are done with line 44, this is the picture. Now, do we know the actual content of these bytes over here? The answer is no, they are uninitialized at this point. Okay, so we have just done the allocation, but we have not done anything with those local variables of main. All right, so next, what do? We can also take a look at the C code because remember, the assembly code is just trying to implement the C code as closely as possible. So the first thing we want to do is to take the address of R, which is an array of 5 bytes, and use that to update APTR. So even without knowing how to do it in assembly code, I can kind of know that, oh, so that means F9, which is the address of R, should be the content at this location here. So this should be F9, after that operation is done. Does that make sense? So just from reading the C code and knowing how the memory is laid out, I know that the location FE should have a content of F9. Now, how is it going to be done? Well, main got it done, but it also got it done correctly. So we switch back to this code here. So that part is done by line 46 to line 50. So if you guys are thinking, okay, so we know what it's supposed to do, we know which chunk of code is supposed to get it done, but do we know that it actually got it done? Well, that's what the trace analyzer is for, because you can actually track all the updates to all the locations of RAM, as well as the stack point. So now we go back here, we go back to, I'm going to move this spreadsheet next to, oh, where's my assembler? Just so that it's easier to switch between those two. So we go back here. This is the return address. And then this is APTR. So we know that FE is getting the content of F9 because of the instruction on line 50. So that is now consistent with what I said earlier, as well as what we think the stack should look like, just based on the C code. Are we still doing okay so far? Just kind of following the update of the locations. Question? Yes.
So yeah, it's F9 because a pointer is a array 0, which is F9.
Because we update APTR with the address of R. The address of R as an array of 5 bytes is F9, because that's the first location of where you find those bytes.
So the first one's the pointer to the array, and the second one in the arrays, that's the array itself.
Yes,
So it points to the first of the arrays.
exactly, as the C code indicates. So the assembly code is really just being super faithful to the C code. It's just doing it in a different way. Do we have any other questions? Because I think it's good to move slowly so that we fully understand what is going on the stack with the stack pointer, with all the variables and so on. Yes,
So in the CT, the other code. So
You
you're
want-
putting main array into A. You're adding D to it. D to A, so you're making it that location. And then you're doing similar to main A pointer. Storing that. So you're just placing those into the stack at those locations.
everything is on the stack. Well, okay, I take it back. Not everything is on the stack because we do have 5 static local variables, but all of the other variables and parameters, they are all living on the stack.
Do you have to now do the other part, the array pointer?
The
Or
array
did you
pointer-
already do the? This. The only supposed
Lines 46 to 50 is doing what line 32 is specifying in the C code. These 5 lines is doing, or they are accomplishing what line 32 is spelling out. Okay, all right. So the next thing we need to do is to call traverse. That's the immediate next thing to do. So when you call a subroutine, we have to push the last argument first, and then we move our way to the first argument, and then we push the return address, and then we do a JMPI to the subroutine. Now, how do we know all that stuff? Tech, did you talk about this? I cannot remember how many times I talked about it. Okay, that's the one part I cannot remember is how many times. Yes, we did talk about it. This is the core of the caller-callee agreement. Okay, so those 2 documents that are linked from Canvas is important because they tell you the contract between the caller and the subroutine being called, and everything that we do. There may be a bazillion ways to do it, but they all have to accomplish that, okay, which is to meet what the contract specifies. Okay, so without knowing the assembly code to do this, we know the address of APTR should be pushed first, which means it should be taking location F8. So now we look at the memory map here. We look at F8. We say, what is that? Well, that is actually array, parameter array, and it is the address of APTR. So this should be FE. Is that okay so far? Because this is, I'm just interpreting the C code, and based on how memory is utilized in the assembly code, I know this has to be accomplished. Now, how is it accomplished? That's a secondary question. I know what I should expect. Do we have any questions about this one? The second argument. So right now, okay, if you're a visual person, you might want to draw some pointers. You might want to draw some arrows around, because this is pointing to this, which in return is pointing to this. In other words, the argument array or the parameter array is pointing to APTR of main. APTR of main in return is pointing to the beginning of R, at least at this point. Are we doing okay? All right. So what about the first argument? What is it? So the first argument is the address of N1, but N1 is not an auto local variable, it is a static, which means all we need is to get to the main underscore N1 as a label, and that is the address of N1. So that means, if I really want to know, I can go to the Assemble tab to find out what it is, because in the Assemble tab, it would actually show you in the label definition. I mean, it doesn't show you exactly, but it gives you the hint. N1 of main is starting at location 05. So we should have that at the next location. So this should be 05. I put a single quote here to turn it into a string, otherwise the alignment would be off. Yep.
Could it be 0A? Because I remember I was running it, could it be 0A as a
Let me go back to the assembler, because I might have moved something, but I don't think so.
doesn't W have the
Right, W has the address. Thank you. I was reading my own spreadsheet wrong. Okay, so that should be 0A. There we go. Thank you. So that points to the node. It points to node N1, which is, really all the way. If you think about this as the memory space, this is pointing to something way down. Okay. All right, and then we push the return address. So we will just say that this is the return address to what? It would be the return address to line 61. Okay, so I can say line 61, or I can find out exactly what it is. The return address is really not important, so it's not really crucial for me to find out exactly what goes into these bytes, because it is just a location that I need to go back to. Are we good so far? Okay. So once I set up everything, I do a JMPI instruction. Okay, so here's the JMPI instruction. And then once we get to the label traverse, we have a halt instruction right there, and the program stops, right? So that means, if I look at the actual trace, if I go to the analysis tab of the trace, it would store F8 gets updated to FE. That's exactly what we expected it to do. Whoops. And then when we scroll down a little bit, we also see F7 gets 0A, which is also what we predicted that it should do, like here. And then it will push the return address, one more item on the stack, and then we get to the halt instruction, and the whole program stops at this point. So I know you're going to say, some people will say that I have not done a single thing to do the homework assignment. That assessment is entirely correct from one perspective, but it is somewhat incorrect from a different perspective. Because knowing what is on the stack and how they relate to each other, and also how they relate to the C code, is a necessary starting point for this entire program. At least I understand what is on the stack right now. I understand why each location is getting the value that it is getting. Are we doing okay so far? All right, it's all good? Okay, so now that I have a verification that I have an understanding of what the stack looks like by the time I get to traverse, I will do the absolute simplest thing that I can possibly do, which is just to return. Okay, so I will do the return code, and it's just the usual sequence, which is LD. If you are concerned that the function may be returning a value, you can always just use register B or register C. Okay, that way you don't have to think about the whole thing. It's like, wait, does traverse return a value? Don't care, because we're just going to use register B or register C. So I'll just go ahead and use register B here. Now I know these instructions at this point looks like a template, but it is still important that you will still be able to explain to yourself what each instruction is doing and what they are doing together. Okay. So I'm just returning back without doing a single thing. But according to this program, it should just terminate, okay? It does not do what traverse is supposed to do, but it should still terminate normally, which means it should return to main. Main returns to the entry code, and then we stop at the halt instruction, I believe, on line 7. Okay, so make sure I save the code because that's something I keep forgetting to do. And it's not doing it. Okay, oh, because I use uppercase and not lowercase. There we go. So we switch back here. And then we rerun the program. We just want to see that it terminates. That's all we want to do. Because occasionally I write some code incorrectly and it may not even terminate. So we go back to the trace. We just go a few more steps and we return to the halt instruction on line 7. And the stack pointer is balanced. So I have a pretty good feel that everything else is set up correctly. So now I can really focus on just implementing traverse. Because unless I know that everything else is set up correctly, it is pointless to try to implement traverse because I might have the wrong stuff on the stack. It may not, after it returns to main itself may do something wonky and it never really exit the program. So now I know I have a good code base to begin with. Now, if I was Ryan Hermely, then I would be teaching you guys how to use GitHub, okay, to do revision control, okay? I will only mention that word in this class because you guys got a lot of other stuff to learn already. But in reality, it is good to have a revision control, type of system so that this way, I'm going to check in the program right now, and I'm just going to comment on that version and say, it is set up correctly. Now we are ready to get started with the actual code of traverse. Are we okay so far? Okay, all right. Okay, so now we go back to the C code and the assembly code, and I have to look at the code that I have to implement, which is not really long, but I don't want to implement everything at the same time, because you might remember the way I kind of describe the process of implementing this program is to do it step by step. Because if you do not do it step by step and the program doesn't work the way you think it should work, it becomes really difficult to find out why it is not doing it. Because now you got what, 20, 30, 40 lines, and you don't know where the problem is. But if I only add, let's say 5, 10 lines each time, I can test that. And then if it doesn't work, I can focus on those 5 to 10 lines that I just added and go like, okay, what went wrong here? So instead of implementing the entire subroutine here, I'm just going to implement the shell of the conditional statement. So I'm just going to say, well, let's go ahead and access PTR, find out whether it is null or not, and do something that I can remember in the middle. I can always just do a 2 no-op instructions or something like that, and that will be the end of it. Okay, so before I do that, it is handy, for me at least, to define the labels. So I'm going to define traverse. It has no local variables, so we can always do this. Okay, we can always just say that LVS is 0. So this way, if later on I say, it's going to be more useful if I have local variables, I can do that later on. So that means, I can always also do something like this, which is totally unnecessary at this point. But once again, it is a template that can help save me time if later on I find out that, well, we actually do need local variables. So I'm just going to do something like this, just in case I end up using local variables after all. Now, at this point, you don't have to do this, okay? If you do not do something like this, perfectly fine, makes sense, okay? But in general, when I'm writing a subroutine in assembly language, I just by default put these 2 in here. I can always optimize them out later. But by putting them here to begin with, I gave myself the infrastructure to use local variables if I need to use local variables later. It's just that at this point, I don't need it. I don't think I will need it at all. Okay. All right, so now we can focus on the actual code, and we need to define the offset to various things on the call stack. So I just have to define traverse underscore PTR as traverse LBS 1 plus. And then we have array, which is PTR 1 plus. So these two labels on line 37 and 38, those are just handy things that I can use, that I can refer to get to the offset or displacement in number of bytes from where the stack pointer points to those two particular parameters from the perspective of traverse. So we have PTR as a parameter. We also have array as a parameter. So I personally maintain the same name as in the C code. You don't have to do that, okay? But I tend to use the same name, so this way I don't have any. There's no translation process needed when I'm working between the two code base. Okay. Do we have any questions at this point? All right. So I'm just going to implement here line 11, line 12, and line 17, which is basically just an empty conditional statement. That's all I want to do right now. So in order to do that, I'm going to have to do an LDIA with traverse PTR, add AD, and then we need a load AA, okay, and then and AA, JZI to the else of traverse. So we'll go, there's no else, so it's just the end if. Otherwise, this would be the then branch of the conditional statement. I stick two no ops here just so that I can differentiate whether it did it or not. And then here we define the label, to mark the end, which is traverse underscore end if. And that's it. That's all I'm going to do. So what I have done so far between line 43 to line 53 in the assembly code is to implement the shell of the conditional statement in C. That's all I did. It has no content whatsoever in it. The content is replaced by only two no-op instructions, but I can tell whether I got into the then branch by looking at the trace and see if those two no-op instructions executed or not. So I can actually check whether the conditional statement is checking things correctly or not. So do we have any questions before I go to actually test the code? Yes.
So 43 to 57 is just the if statement and PTR. If pointer.
Line 43 to line 47 is corresponding to line 11 itself, more or less.
And can I very quickly see the stack representation?
The stack representation. The stack representation would not change. This would stay constant for a while. Oh, right, 1 tab. Yep.
So traverse of PTR is 1 over the stack pointer.
The stack pointer currently is not here anymore. The stack pointer is currently here.
So currently the traverse levels is still technically pointing to return address. We're going to change that later.
Say that one more time, please.
Traverse LVS.
Yes.
Stack pointer 0. So it's currently pointing at that.
The stack pointer points to location F6 right now.
Yeah. So 1 up is the traverse pointer.
It's the PTR parameter, and then 2 up would be the array pointer. Array. Yep. So this is indeed correct. This is exactly what we have for the entire duration of executing traverse, at least at the time. All right. So now it's time to test the code again. But to test this code, if you remember, I said, don't test it with main N1. Instead, test it with something that's more predictable. In other words, test it with a null pointer. Because we want to know, there's one thing we really want to know is the recursive call will terminate correctly. And that is the condition to terminate the recursive call. So this will be the first thing I check, is to make sure that, yep, if I give it a null pointer, it's going to stop. So So we'll go ahead and test this code, make sure I save the file first, right? Because I keep forgetting to do that. And then we'll go ahead and just test run this code. And then we switch back to the trace analyzer, right? And the trace analyzer would not tell you directly whether we got into the conditional branch or not. But then if we switch to the assemble tab in the assembler, then we can have a way to check that. Because if the conditional branch did happen, and looking at where did I put traverse? There we go. So if this JCI did happen, then we would have jumped from location 2.1 in column A straight to column location 2.5. It would not have gone through location 2.3 nor 2.4. Does everybody understand what I'm talking about? Because I want to see if the program is working or not. Does it successfully check whether pointer is null or not, and do absolutely nothing if it is null? That's what I want to check. So I now know that, hey, if this JCI happens, then it's going to go from this instruction at location 2.1 straight to the LDID, execute on at location 2.5. So I can now go to the analysis tab because I just ran the program and just kind of follow that. Okay, there are quick ways to check this because you can just look at this is location 2.1, it is executing a JCI instruction. This is location 2.5, which is the exit code. The two no-op instructions did not execute. That is the predicted behavior. This is good. Now, just because it can handle the null pointer correctly does not mean that it can handle a non-null pointer correctly either. So I need to check the other way and say, what if I give you a non-null pointer? Are you going to go into the then statement to execute those two no-op instructions? I need to double check that too, because otherwise I can have the code incorrect and it just skips regardless. That is entirely possible. So I want to double check before I move forward. So writing this program is a very iterative process. It is not intended to be a single session. I'm just going to sit down, write the code from beginning to end, and I'm done. Yeah, there's no way it can be done like that. And you will encounter many programs with enough complexity that you can't really just write a program from the beginning all the way to the end and expect it to work the first time. All right, so we switch back to the code analyzer, and this time it did execute those two no-op instructions. So now we know, okay, so the conditional statement is working. Very good. But I want to check one more thing. Did we actually access pointer? Because I could have passed something because it's just checking whether it's null or not. But because we know register A has the value of 0A, which is what PTR is supposed to be. So we now verify also that the parameter is passed correctly from the caller. It is also accessed correctly from inside the subroutine. So now I have confidence to implement whatever is inside the then statement, knowing that, yes, I know what the stack looks like. I know how to get to the parameters. I know the conditional statement itself is working. So all of those are really important things to consider because if I cannot confirm any one of those items and just blindly go into the then statement, I'm just asking for trouble because if it doesn't work, I have no idea why it is not working. Are we doing okay so far? Any questions? Okay, all right. All right, so we are going to go back to the editor. And then we'll go ahead and go back to traverse. Okay, yep, there we go. And now we can just go ahead and start to implement whatever is in the then statement. We'll start with line 13. Okay, line 13 is a recursive call, and I'll just do one recursive call. I'm going to forget line 14 to line 16 in C entirely, at least for now, because I need to know that I can actually do the recursion. It starts at the right time, it comes back, and it goes all the way back. Okay, so that's what I need to confirm first. All right, so we'll just focus on line 13. Line 13 says we have to pass array. So I'm going to use indentation here just to indicate that we are in the then statement. So this way it is easier, or visually it's easier to identify that this is a part of the conditional statement and it is not outside of the conditional statement. So now we have LDIA with traverse array LAD, and then we have to push it on the stack. Oh, wait, we have to do an LDAA, and then we push it on the stack. There we go. And then we have to pass the L member, the value of the L member of the structure that PTR points to. Okay, so how do we do that? Well, kind of the same thing, right? So LDIA with traverse PTR, but this time I need a 1+ because we have just pushed one additional item on the stack. So the stack pointer is no longer at the same place as it was at the entry point of the function. It is now pointing to 1 byte lower. So that's why I need this 1+. Where did I put it? Okay, right here. So I need to put that 1+ here to compensate for the extra byte that I just pushed. And then we do add AD. And then, I mean, there are ways to save some of this trouble here because your register A already has traverse pointer. Yep.
So every argument we're pushing after the first, after traverse array, we would add 1. So like if traverse has
Right.
3 arguments.
Yep.
We just keep adding 1.
That is correct. Now, there are tricks we can do so that you don't have to do that. I'll show you a trick, okay? So I will show you a trick so that we don't have to do that. In other words, okay, so I'm going to do some optimization here. I will use register B for that purpose. And then register A continues, oh, okay. That would not help. Okay, never mind, because this is still correct, but I want to show the point that I want to make. So at this point, okay, if I change the program to be like this, at this point, nothing is pushed on the stack. So that means I need to use another register because if I use register A, it will clobber or overwrite the value of register A. So, but I can use register B to kind of do this. And then we, let's see, we did a LDBB. So now register B is pointer. Pointer is the address of a structure. I'm not interested in the entire structure. I'm interested only in a member of that structure. So I have to add the offset from the beginning of a structure to the member that I need to access to whatever is in register B. And I have just enough registers to do this. So register C is going to be node underscore L in this case. And then I just add B or C, doesn't matter which way, so we can just do BC is fine. Okay, so at this point, without changing the stack at all, without pushing anything, between line 50 and line 58, do you see any change to the stack pointer? We use the stack pointer in the add instruction, but we are not changing the stack pointer. So that means I have not changed the displacement or the number of bytes between what the stack pointer points to and the various items on the stack. So that is why this time, in this particular version of the code, line 54 cannot use the 1+, because that would actually make it wrong. Are we still kind of doing okay at this point? Yep.
Stick to this version of the code, where you're just putting it in the registers and not putting it on the stack.
Say that one time.
Are you going to stick with this version of the code? You're only keeping it in the register and not on the stack.
What is the scope to which you're referring? Like just here in this program or in general, in the final exam?
When you're for the rest of this
Discussion?
Yeah.
I don't have to. I'll do it like this way right now. The whole point is there are many ways to get the same thing done. This is one of those many ways. And that's all we need to know is, oh, okay, in this particular context, it works. Okay. So now I have all the time in the world to decrement D, STDA first, okay? Because that's our second argument. And then decrement D again, STDB, because that's our first argument. So this is a kind of a tricky way to avoid having to adjust for things that they've pushed already, because I just pre-compute the things that I need to push. I have enough registers to keep those things around and then just push those things on the stack, so I don't have to adjust the offset to the displacements. All right, are we still doing okay at this point? All right. So what is left is the usual call sequence, and I'm just going to use the usual one that I use in this class, which is putting the LDI in front of the decrement. And then we just need a JMPI to the subroutine that we are calling, which turns out to be the function that we are in already. But that should make no difference whatsoever in the implementation of the call. When it returns, I have to increment the stack pointer twice because I have two arguments, or I have 2 bytes worth of arguments on the stack. This will clean it up. And I'm just going to say, yeah, this is all I want to do. In other words, I only implement line 13 without any of the other lines. The question is, can I still check to make sure that this program works? That would be the next question. Question?
I was just gonna say, are you gonna give me the stack representation?
Sure. We'll go ahead and update the stack representation, but it becomes, I cannot update it unless I know which test case I'm using. So, okay, so this is going back to something that I said before. Question? Oh, okay. So this is going back to something that I said before. So how should we test this code? It is recursive. Recursive code can be a little bit tricky to debug, but of all the possible test cases, there are 2 particular test cases that can help you quickly identify, yep, you got it done. So out of the 5 nodes, which 2 would require only 1 level of recursion and it just returns right away?
And 4 and 5.
Yep, N4 and 5.
Can we do N2 as well?
Hmm?
Can we use N2 as well?
You could use N2 too, because N2 also has a 0 or no pointer for the left. But N4, N5 has nodes for both of those, the left and the right. So we can basically use it to check both of them. Okay, so that's what we would use to check the program. And so we are changing the test case here again. So I might as well just put some comments here and say, change the following to use different test cases. Okay, so we're going to use N5. Okay, so now if I change it to N5, you have to know what is supposed to happen. Okay, so we'll go ahead and go back to the stack layout and find out what the stack should look like at the deepest point of the recursion. So we'll switch to the picture here. So in this case, we are using the address of N5. And it's doing a recursive call. So that means we are going to push array again. Array is not changed. It is still FE. But this time, this particular PDR, what should that be? We still have a return address. Okay, so we'll say return address to, but this time it's not to line 61 anymore. This time it is going to line 110 at this point of this code. Okay, but the biggest question is what should go here? This should be the L number of N5. What is the L number of N5, both in the C code and in the assembly code? It's a 0. So that means at the deepest point of this execution of the program, I should expect this on the stack. Now, you can always look up the return address, to fill in exactly what should go into F3, location F3, as well as location F6, but it's not important from the perspective of, the parameters and local variables. Is that okay so far? We good? All right. So I will run the code, and then we'll go back and check whether that is what we got or not. So we save the file because I keep forgetting, and then we run the code. This is a very iterative approach, and we can afford it. There we go. So now we go back to the analysis tab. And now the question is, how do we know this works or not? Okay, so I'm going to ask you guys, do you have any idea? What is the strategy to check to make sure that this code works? And how do we get to the point of checking that? Well, we know what is supposed to be on the stack, don't we? Okay, let's go back and take a look at what is supposed to be on the stack. This is what is supposed to be on the stack. So that means something has to put this 0, 0 into location F4. So knowing that, how do you quickly locate that? Yes, I see that location F4 is updated to 0, 0. What is the quickest way to do it? I have illustrated that approach a few times in the class too. It's a Google Sheet thing.
You did I don't remember, but like the search and then search.
Yep, so you go to the spreadsheet, you go to the column, it's easier to highlight the entire column, which is column C in this case, and then you search, okay, go to edit, say find and replace, and I use regular expression, you don't have to, so if you just say you'll find F4 equals to, that works too, okay? So we just click find, go like, oh, whoa, that doesn't look right. So that means I pushed something incorrectly in this case. Did I change the main to use N4, N5, or did I? I did not, did I? I think I did not. Okay, let me just double check the code. I did. Yep.
Do you need to load PTR? Like you add the actually. Like
You mean in Traverse?
yeah.
Okay, so this is good because the program is not working.
Yeah, you can load.
Okay, so let's go back to main first. I was double checking to make sure main is using N5. It is using N5. So that means, what I expected to be a 0. This is supposed to be a 0. It is a 17. All right, so I'm just going to pause right now and go like, okay, but how do we fix this problem? So the way we fix this problem, or the way we find the problem is, why are we pushing a 17? Well, where's the 17 coming from? It is coming from register B. So why is register B 17 at this point? Register B was last updated here. So this is node L, and we are adding to register B, which had pointer. Okay, so let me scroll up a little bit here. This is the debugging process. And this is also why I said, if the program doesn't work, it's even better from the perspective of understanding the material. Because now I really have to kind of go back here and say, okay, so the template seems to be fine, but why is it not working? This is the offset of PTR. This is the address of PTR. This is PTR. This is the offset to a member that PTR is pointing to. This is the address of a member that I want to access. And I have done no changes outward. I have just pushed the address of the member L of N5 on the stack. Is that what the C code is calling for?
You want the value.
I want the value, exactly. So what am I missing? a dereference in this case is a load. So what I am missing in the computation of B. Going back to here. Okay, so we are looking at this one here. We are missing a load BB. Because on line 58, I would have computed the address of member L of the structure the PTR points to. I got everything right at that point. But we don't want the address. We want the value of the member. That is the reason. But do you see how the trace allow you to kind of quote unquote execute a program backwards? Because you see, oh, that's wrong. Okay, that's not the right value that we should be pushing. That means B has the wrong value. If B has the wrong value, who gave it the wrong value? You go backwards. Okay, you go like, whoa. Okay, we computed the address of the member, but we never dereference because we're supposed to get to the value of the member. Okay. So this is why I actually spent a bit of time to make the trace analyzer and all that stuff, is to help you guys debug your program. If you did not use that feature, then you're missing out, a really useful tool to help debug and also to help visualize the program. Now, I know some of you probably used the feature and you still could not find all the bugs. Well, that's understandable. I mean, the program is a little bit complex. But the point is, if you did try and you did use the tool to kind of look at, okay, what is the register value here? What am I writing into RAM and so on? That helps you understand the caller-callee agreement and also how to get things done. So that by itself is studying for this class. There's no separation between, oh, this is homework and this is studying, this is the exam. The homework, the programming exercise, the experience of using the debugger is studying for this class. All right, so I just fixed the program and I better double check and make sure that this fixed the problem. So save the code, run it again. If anyone is curious of tech, do you ever use an IDE? The answer is no. I consider Vim an IDE, sufficient IDE. All right, so now we change the code a little bit. Oops, no, press the wrong key. All right, so we are looking at F4, so we just have to scroll down a little bit. Aha, okay, so this time we got a 0. But wait, we also want to make sure the program behaves correctly. So that means, after this point, after this last call, we have to push one more thing, which is the return address. This is the return address. I should not see the stack pointer go any lower because this is the termination of the recursion. Does that make sense? So at this point, if I just want to skip a bunch of stuff, I should only see the stack pointer going back up. Okay, so you can see the stack pointer is here. It's going back up to F4, F5, F6, and it should go to F6 and then F7. So the program is now going back up to main, and then at some point it's going to return. Are we still okay at this point? So what have I done so far? Not really that far, but I know the program does work. The recursive call is working. I can access all the parameters correctly. So now the next thing I'm going to do is to implement line 14. I'm not going to do the rest, okay? One thing at a time. That is important. Do one thing at a time. So I'm going to implement line 14 and we'll just move it down here, okay? So this is after the first recursive call. It is the right time to implement line 14. Line 14 has a slightly more complicated right-hand side. We'll deal with the right-hand side first, and then we'll deal with the left-hand side. So the right-hand side says we need to get the pointer, LDI, reverse, pointer, need to specify the register. And then we do an add AD, and then we do an LDAA. All right, so we have the pointer, which is now the address of a structure. But I don't need the entire structure. I want to access a particular member of that structure, which is the value. So we do a LDIB with node underscore value, which is the label representing the number of bytes between member value and the beginning of the structure. So I just have to add these two together. Whether I do an add AB or add BA really does not matter. I'm going to do add AB in this case. And then now I learned my lesson, right? Remember to dereference it, because otherwise I have the address of a member of a structure that is pointed to by PTR, but I really need the value of that. So, okay, so there's that. And then on the left-hand side, I need a double dereference overwrite. So, but before I can do anything else, I need array. So we'll do LDI. So register A cannot be used anymore, but register B and C can both be used at this point. So I use register B, traverse underscore array. And then we do a add BD to get to the address. And then we do a LDBB to get to array itself. So at this point, register B is array without any dereferencing. I need to dereference it twice. What should I do? Oh, LD it twice. No, LD it once, and then ST it once. Because LD is dereferencing in the read sense. ST is dereferencing in the write sense. Okay, because one is overwriting. Anytime you have the parentheses around a register, it is dereferencing. That is why I chose that syntax to highlight, hey, this is not just the register. You're not changing the register. You're changing what the register is pointing to in RAM. That is what the parentheses are trying to emphasize. Okay, so that means we need one more of these and then one of these. Okay, so I just wrote how many lines? 11 lines, okay? So I go like, okay, I better double check that this is working before I go any further. Okay, so now we save the file first. And then also what we want to do is to find out what it is supposed to do. I'm still dealing with N5. The value of N5 is a 9. And array, okay, so let me go back to the picture of what the stack looks like. So at this point, array points to location FE. That's the first dereference. This in return points to location F9. This is where it should get the 9. 9 should go here in this particular test case. And this one here does not do a single thing because the second or the recursive call of traverse would get a null pointer, which means it's going to skip over the entire conditional, the entire then statement, which means it's not going to do anything to array in main. So this is what I'm expecting. Okay, once I change the program like this, I'm expecting location F9 to get updated with a value of 0.9 because that is the value member of N5. Are we doing okay so far with that? So this is important not only in this class, in every single class that has any type of debugging and programming, and possibly in your career. When you're debugging a program, the first thing you need to do is you need to know what the program is supposed to do. Now, is it going to look like this? No, it's not going to be a table. Most of the time, you're dealing with something that's much more complex, okay? It's probably a structure of some kind. You want to look at the JSON structure and so on and so forth, okay? But you still need to make sure that you know what the program is supposed to do. Otherwise, there is no way you can debug the program. Is that okay? All right, so let's go ahead and check out the program and see whether it is getting this done or not. This particular iterative process is useful because I was able to catch a bug earlier, because if I didn't catch the bug, the program would have done the recursion endlessly, and I would not know what to do. If I continue to write the program, it would not be helpful at all. But at least right now, I know that if anything goes wrong, it would be the last 11 lines that I added to the program. All right, so we got back here, and if I want to be super lazy, I'm just going to go to column C and say, okay, show me how location F9 gets updated. I should be expecting it updates to 09. So we go to find and replace, look at location F9 and see how it is updated. Find, yep, okay, that's all good. And just to make sure that I didn't mess up anything else, I also want to make sure that the entire program exited correctly at the halt instruction on line 7. I'm not sure why it's not showing the program code anymore. I think I did something. There we go. I messed up my own little formula because I typed something in that column somewhere. Okay. All right, cool. So we only got one more really tricky thing to do because the other recursive call is pretty much the same thing, except replace member L with member R. Okay, that should not be too challenging. So the only thing that is somewhat tricky to do is, okay, going back to the code, is line 15, okay? So line 15 has to add one to the right thing, okay? There are a few possible wrong things I can do here. I can be adding one to the parameter itself. I can be adding one to, I guess, something else. I can only think of that's the only thing that can go wrong is I'm just adding one to the parameter. But instead, I should be adding one to whatever the parameter itself is pointing to. Okay, so if that is the case, what should be incremented? So now we go back to the stack here and say, all right, so this here, I'm not supposed to increment the FE to FF. I'm supposed to increment what the location of FE, which is right here. So that means this F9 should change to FA. Okay, so I'm just gonna indicate that this, I should see an update here from F9 to FA. So let me pause here and see if there are any questions about why that is the case. Because array is a pointer that follows the pointer, it points to location FE. And according to the syntax, we are incrementing whatever array is pointing to, which is whatever is at location FE. It had a value of F9. I should see that update to FA. Is that okay? We good? Okay, all right. So we go back to the assembly code, and then we try to implement line 15. So line 15 still needs array, okay? So I'm going to recompute everything. I'm not trying to save or optimize any code here. So LDIA with traverse array, add AD, LDAA. So now I have array, the parameter, the value of the parameter array in register A. Okay, cool. But I need to change whatever it points to. I need to increment whatever it points to by 1. So that means I don't want to destroy register A because I still need that location, but I also need to know what is the content at that location. Well, fortunately, I got a few registers. So register B is whatever array points to, which in C is asterisk array. Okay, so I'm just going to type some documentation here. There we go. All right, so that is supposed to be incremented, and then I need to store it back to whatever array is pointing to. So now we are updating array to array, whatever array points to, plus 1. Well, at least I suspect this will get the trick done. How many lines am I adding? 6 lines. But I'm going to test the code again. So this is a very repetitive process. It would appear that I'm wasting time because I'm doing a little chunk of code, test a whole bunch, theorize, making sure that it's working. But in the end, I'm actually saving time. And this approach does not only apply in this class. This is the second time I said that in this class, but I just want to make sure that people understand that. Years ago, I went to the racetrack. I went on to track day because I had a really old beat up Miata. which is great for handling, but on the straight line is slower than my minivan. And then what I learned, the first thing I learned, okay, you guys are going like, okay, you're talking about, driving a car in a racetrack. What does that have anything to do with programming? My instructor said the first thing was to learn how to drive fast, drive slow first. Because you have to learn the track, you have to learn the apex, you have to learn the transmission, you have to learn all of those things. If you're going too fast, you're going to miss all of those things. So you got to go slow to learn how to go fast. All right, so let's see whether we are going slightly faster this time. Sorry?
No, I said, like, now you're speaking. I'm like,
Yeah, we have some of those, really high-end, brand new, GTI and whatnot. And the first time they get on the track, they just like that. Oh, look at that. He's in the sand now. No harm done except a bruise to the ego. All right, so we're looking at F4, F9, FE needs to be updated a few times. Okay, maybe, okay, I'll just kind of focus on the column C, and then we use Control H. I keep forgetting the shortcut key. Okay, so we want to see how FE is updated. So you'll find, yep, it updated to FA. And then the other time it was F9. So that's the first time because it's on row 25. And then the second time it is updated on row 148 to FA. Okay. And we got 3 minutes left. Do you think I can get the program done? We'll see. We will see, right? So what I do is I just need to go back to the first call, right? The first call is from line 50 to (50 to 73). So line 50 to line 73, yank. It's the same thing as copy. And then we go here and then we paste and do one thing. This time we need member R. Save the program again. And this time I think I'm going to go for the entire thing, just because I'm running out of time. So we'll go with node 1. So now with this code, it is now identical to the C code, which means when you run the C code in GDB or online GDB or CodeBlocks or whatever IDE you use, whatever content that you found in R in main should now be found from location F9 to location 9A, B, C, D. Okay, so that's what we are expecting. All right, make sure we save the code. Yep, we did. And then we submit the code. And by the way, I just got my performance review today. So I do thank all of your feedback. And don't worry, I don't get to see your evaluation until after the final grades are due. All right, so now we need to check, right, a whole bunch of stuff. The first thing is, what is F9 getting? What is FA getting, and so on? Okay, so this time, it makes sense to do a little bit of a regular expression because we are checking multiple locations, so I can use one simple search to find all of those. So we will check regular expression. So we're looking at asterisk F, and then we're looking at location 9, A, B, C, D. Those are the 5 locations that we're interested in. And then we click find. Okay, so we got 3, 4, 5, 9, and 10. And that is exactly what the C code should give you. And double checking, we want to make sure that I did not mess up the program by accident. So we need to double check by going down, make sure the program does halt in the end where it is supposed to halt. And we did. And the stack pointer is also been getting back to 0, 0. So everything is squared away. So just in time. And I did not time myself today. I actually did not plan anything for today's lecture.
Won the race.
Hmm?
Won the race.
Well, I got to the finish line at exactly the time that I want to cross the finish line. This does not necessarily mean that I won. It's just that I think I won if I were to drive a bus because I'm confident. All right. So there's no lab activity left to do. But if you want me to take a look at your program because you're kind of stumped, why your program is not working, or you want some explanation, I can do that. I'm obligated to stay until 8:20. So I will head out to the lab. And if nobody shows up, I'll just kind of hang out by myself over there for a while.
I'm correcting